Hello there. Today we're going to be talking about Poisson disk sampling, which is a method of generating points that are natural looking, they're not too close together, and they're not too far away. So let's dive into it. Alright, so this slide is the first algorithm that you might think of, which is you generate a random point, and you check its distance to all other points, and if it's not too close to any other point, then you keep it. If it is too close, then you don't keep it. But as you can see, it's getting really slow already, and this is not even many points. Alright, so rather than using that very slow algorithm, we're going to be using this one by Robert Poisson from the University of British Columbia. And this is actually one of the shortest papers I've ever seen. What we want to do is we want to create points that are close to each other, but not too close. And then we want to make that very performant. So rather than checking all of the points, we just check for some of the points. Alright, so before we go into the writing of the code, I'm just going to show you what's in these three files here. There's a v2 file, which is just a very simple vector2 module. It's just got a type vector2 with a float x, y, and a couple of helper functions, distance, square distance, and just a comparator to compare if the two vectors are the same. And if we have a look at this one, math.h, this has a few things which C doesn't have usually: max, min, pi, and this is a random float function. It's just going to give us a float between the minimum and maximum that we define here. And the last thing is list. This is just a really simple linked list. You can add, you can remove, and you can get by index, and that's it. Alright, so the first thing we need to do is choose our dimensions. So this algorithm actually works in n dimensions. I haven't actually tested it in anything but 2 dimensions, but I'm going to take their word for it. So let's just define that here as n equals 2. Now we need to choose a minimum distance, which is how close points can be before they're too close, or rather the minimum distance they can be away from each other. So for that, I'm going to choose a distance of, I don't know, 20, just arbitrary. And the next thing we need, as it says here, is we need to choose the amount of samples before a rejection happens. So this will make sense later, but for now we'll just leave it as their suggestion of 30. Alright, and the last thing we need is this thing called cell size, which is actually in step 0. We picked the cell size to be bounded by r over square root of n. So this I'm going to call w because it's the same as the width of each square of each cell. And we're going to just set that up now to square root of n, r divided by the square root of n, and actually this needs to be a float. Now we've defined our constants, we can calculate a few things that we're going to need. So we're going to need to know how many columns we have and how many rows we have of this grid. So let's have a look at that. We're going to do this. The columns is, we're going to using ceil here because if you use floor, you might end up with the last column being slightly less than the edge of your width, whatever your width is. And actually, we haven't even set width, so we should do that. So I'm going to say our width is 640 and our height is 360. These are just common, it's a common resolution for pixel art games, which I like. And it's also a 16 by 9 resolution, so yeah. So this is calculating the columns and rows. That's going to be useful. So we've got the columns, we've got the rows, and we can move on to step 0 here. So in step 0, we're supposed to initialize the grid. So now that we've got the amount of columns and the amount of rows, we can do that. So we're going to say the grid is grid of vector 2s. And actually I'll use calloc so they're all zeroed. And we'll say that is cols times rows times size of grid. Okay, that's going to give us a grid with a whole bunch of vector 2s that are all 0, 0, 0, 0x and 0y. And it says that we should initialize this to an array of integers with a default of -1 that indicates it's empty, but I'm just going to consider a vector of 0, 0 as empty instead. Of course, if you're using this to generate something and you're using negative numbers, then it might be the case that you have 0, 0, and also this might not work, etc., but for our case, it should be totally fine. Okay, so it also says that we should be using an n-dimensional array, but you can actually just use a one-dimensional array and then calculate how far along the one-dimensional array it would be for some x and y position. That's step 0 done, actually. So we'll move on to step 1. If I can spell. I cannot spell. Step 1, there we go. Alright, so step 1 says that we should select the initial sample x0, randomly chosen uniformly from the domain. So that just means randomly generate a position, an x and y position. So we're going to do that. We'll just call it position, and we can do this nice, I don't know what you call this, initialization, because we're using C99 instead of 89 for once. And we're just going to generate using our randomF function, randRF, between the width and the height. There we go, we've got a position. So that's that done. And we need to insert it into the background grid, which means we need to figure out whereabouts in the grid it would be. Okay, so here we are in Milton. I just need to draw a little diagram to make it a bit easier to understand. So, let's say we've got a grid like this. Alright, so it's a 5x4 grid. Now, we can say the index of this is 0, 1, 2, 3, 4, etc., etc. Let's say we want to get the position of, or the index rather, of this. The way to calculate this is pretty simple. We say 2 plus 2 times the amount of columns, which in this case is 5. 5. So 2 plus 2 times 5 equals 12. And that coincidentally is here. That's pretty cool. Alright, so now we want to get the column and row that this position is. So we'll just do this. We'll floor the position x divided by the w, which is the cell size. So that will give us the column, and then the row, we're going to say same thing, but with the y. Now we have that, we can use that little formula that I just showed you, and we can add this position to the grid. There we go, that should be right, yep. Why is this complaining? Alright, there we go. So, that's going to add the position that we just created to the grid, so that's select the initial sample and insert it into the grid. Initialize the active list with an array of sample indices with this index 0. So we're going to do something a little bit different. We are going to initialize a list. We're going to call it active. And then we're actually just going to store vectors in here as well, instead of storing integers that refer to array indices. We're just trying to make it as easy as possible for us right now. Maybe not as efficient as it could be, but certainly much more efficient than what it was before. Okay. So now we've got this active list. We've added the point to the list. And that's it for step 1, pretty much. Now, step 2, just move that out of the way. Now you can't see what I'm moving, but anyway. Step 2 is, this is the real meat. This is the meat and potatoes of the whole thing, and it's going to be the largest part. And I've actually written this out a few different times, a few different ways, in a few different languages, just to kind of really cut my teeth. But we're going to be going through a very, very simple implementation. Well, I hope it's simple anyway. So I'm going to say while the active list is not empty. So while 0 is not equal to active length. You could also say while active length is greater than 0, I guess. That's probably a bit more readable for most people. What do we do? We choose a random index from it, say I. I'm not going to call it I because I always use those for loops, and I'm going to be using loops. I'll call it active index. Active index, and we're going to get a random one, so we'll just do random modulo active length. And that will actually give us a random value between 0 and the length of this array, which is handy. What do we do now? Generate up to k points, chosen uniformly from the spherical annulus between radius r and 2r. Okay. Yeah, that sounds confusing, but it's actually very simple. Let's go back to Milton and I'll show you. Oh, actually, I had a slide for this. Is this visible? Yeah. Alright, so this slide. So this donut shape, this blue ring, is actually the annulus from the point, well, the point in the center. So the radius shown at the top is the distance from the point to the inner ring, I guess. And then the double that is to the outer part of the donut. So that's really what this is. So this, let me go back here. This, choosing a point inside the spherical annulus between r and 2r around xi seems complicated, but I'm going to draw an example as well. Let's do that. So, circles. I can't really draw circles well with a mouse, or even without a mouse, but let's say this is our point. And then this is r, which is our radius. And then this is 2r. Okay, now we've got a circle like this. We've got a circle like this, as you saw in that slide. So this area is where any point could be generated. So we choose an angle at random, let's say up here, and then it could be any distance from here to here, and we just generate a point there. And then we check from any surrounding points whether the distance from any surrounding points to this one is greater than or less than this radius. Right, so we'll get into that shortly, but this is basically what that means. Well, since we're in C and we don't have any helper libraries or anything, really, at the moment, we're going to do this just, I guess, the old-fashioned way, if that makes sense. So we're going to get the active point as well. We're going to say that is get by index list. Our list is active. Our index is active index. All right, that's going to give us the active point, and then we want to say a loop here, and this is where we do our samples loop. So we say if I is less than k plus I. All right, now we need to calculate our sample point. So the easiest way to do this is we need to calculate first an angle, so we'll do that. well, this is very easy actually. We'll just do random between, random between 0 and 2 times pi. Because we're using radians. And what else do we need? We need a distance. We'll calculate that distance, and we'll use that random range float. Distance is between our r and 2r. Alright, so now we're going to need the x and y positions, which we can calculate using some simple trigonometry. And we're going to calculate them from the active point. So we'll say active point x plus distance times sine of the angle. That'll give us our new x position. And then our new y position is going to be the same thing, but using the y and using cosine. Alright, now we can assign these to a new point, which we're going to call sample, or a new vector 2, whatever you want to call it. Alright. Now the paper actually says that we're supposed to check for if it's close to the existing samples using the background grid, blah blah blah. Which we will do, but the first thing that we want to do is actually go back here, and we want to check whether it is off our canvas, basically. So we've got this width and height. If it's greater than the width or greater than the height or less than 0 on either of the dimensions or either of the axes, then we want to just continue, or rather not continue. We want to cancel this one. So we're going to say if x is less than 0, or y is less than 0, or x is greater than width, or y is greater than height. Continue. So we're just going to skip this, and it's going to increment the k counter, and it's going to count as one of our tries. So that's going to be a failure. That's fine. Now, the next part is where the grid comes in. So let me do a little bit of explaining about that. Alright, here we are. I've got this little diagram thing set up, and all these slides will be available on my website. I'll put a link in the description. And what this is showing us is, if you look at this circle, this is our circle with the radius of r. And then these are the cells that we've made. This is the grid. Now, if you have a look, anywhere I move inside any particular cell, you can see that the circle covers the entire cell, which means you can only ever have one point per cell. That's one thing. Another thing is, if I move all the way to the edges, you can see that the radius never exceeds this 5 by 5 area around the cell. So that means, rather than checking every single point, we can just find out which cell a particular point is in, and then check the 5 by 5 area around that particular cell. And if any of these have points, we can check the distance to our generated point. That means we go from checking n points to checking a maximum of 25, but most likely less than that. So yeah, let's get into it. Go back to the paper. Alright, here we go. So the first thing we want to find out is which grid cell we're in. Means we're going to need to calculate the column. We can do that same way that we did up here, B and Q. So we're going to use the sample.x divided by w again, and the row is floor of sample.y divided by w. Now, the reason that I've used column and row here is because we're going to be using the P and Q in a second. So maybe for consistency's sake, I should change it up here. But, you know, I can do that later. All right. So now what we want to do is we want to find out. Let's go back to this grid for a second. This one. This one. So let's say we're here. Now we need to find out from here which square is the top left and which square is the bottom right. That's kind of our area. And if you see, when I move to the edge, this is actually a smaller square. So we're actually only doing a 3 by 3 in the top left corner here. Oh, there we go. Yep. So we're going to need to account for that as well, because you don't want to be trying to find out the value of things that are outside of the grid, because that won't work. Okay. So we're going to get P1, and that's going to be the maximum of 0 and the column minus 2. Let's just fix this spelling mistake here. Alright, so that's to prevent us from going outside the grid, this max function. So we're going to do the same thing for P2, but it's going to be the minimum of the columns minus 1, and then the column plus 2. Yeah, so this is the horizontal squares, start and end of the horizontal area. Now we're going to do the same thing for Q1 and Q2. Except instead of columns, we're going to be putting rows. Alright, there we go. And now I'm going to set a variable here called collision. I'm going to set that to 0. And this is going to be to keep track of whether or not we've collided with any other points. Now, we're going to be doing some nested for loop shenanigans. This is where the P comes in. So, we want to say if we're within this 5 by 5 area. So I'm just going to type this out. It should be pretty self-explanatory. Okay, so this is going to give us our 25 cells to iterate over. Now we want to get the index of each cell. I'm going to use that formula from before. And then we want to get the point is in each one of these. So if there's nothing in here, it's going to be 0, 0 for the x and y value. So we can say if there's nothing in here, right, then continue. So we're going to say if the vector to comparison between point and sample is 0. So 0 means it's the same. I'm just copying C's kind of way of comparing things. Then continue. Yep, I don't need that. Alright, now the last thing we want to check is the distance. So if we pass these two, then it's possible that we could find something that's too close. So we want to check the distance from the point to the sample. If that is less than the radius, then we want to say we have a collision. And we want to break out of this loop. Because if any of the points are too close, then there's no point continuing. Alright, now after that stuff is done, we can say if, let me just move this up a bit, if there was no collision, then what do we do? Well, if a point is adequately far from existing samples, admit it as the next sample and add it to the active list. After k attempts, no such point is found. Instead, remove it from the active list. So, since we didn't have a collision, we're going to add it to the active list. We're going to get the index, not times. And we're going to add this one. You know, it's funny, we actually do this twice. Oh, no, we don't. Never mind. Grid index equals sample. There we go. So we've added it to the grid. Now we need to add it to the active list. So we're going to use the list add function from that very simple list that we've been using. And we need to add it to the active list, and the data is sample. There we go. And I think that's it. I'm going to break out of here. Okay. And the last thing we need to do is, if after k attempts no such point is found, remove I from the active list. Alright, so we don't actually have a way to check for that. So up here we'll add found equals 0. And here we'll just add found equals 1. And then out here we can say if not found, we want to remove from the active list the sample. Gonna work? No, not the sample. The active point. Yeah. That's a pointer. Yep. And that should be it. That should be a fully working example, but of course we need to check it. So I'm going to write a little print function down here. I equals 0. So I'm going to print this out as, is that right? 0f. I'm going to print this out as array, no, not array, JavaScript tuples. And then we're going to actually paste it into this page we've got here, what I made this for. So as you can see, we've got 1 point in here, right there. And if we add another random point here, you can see it should update. There we go. All right, so printf, yep, so we need to get the grid I.x and grid I.y. Okay, this, if everything is good, should work. That's not going to work, apparently. Oh, this is definitely not going to work. This is going to give us the wrong thing. You know, I know some people argue against language servers, but they're kind of useful for catching things like that. And like this. No, I didn't mean... This doesn't say samply. Use of undeclared identifier samply. Oh, I used it down there. There we go. And this is complaining because too few arguments, because I used calloc. Alright, there we go. So, it's the moment of truth. Let's just open up a new little window here. We'll run make. And here we go. Nice. It looks like it worked, but to actually test it, I'm going to pipe that into clip.exe and paste it in here. There we go. Nice. So as you can see, we've got some very nicely distributed points. I just got to double check something. Yeah, We didn't actually seed the random number generator, so if I do this again, whoops. Yeah, it should be the same, right? Yeah, there's like this little pattern down here. If I do it again, is it going to be the same? It's going to be the same. Yep. Okay, so make sure that you seed the random number generator. I usually just do this. Okay, now if we make this and run it again, this should be different, hopefully. Yeah, there we go. Alrighty. Alright, if you've made it this far, then I'm going to show you what this is all for. A while ago, I started reading this blog called Red Blob Games by Amit, I've forgotten his last name, Amit Patel. This is an amazing website, and I will have it linked in the description, for learning a whole bunch of stuff about things to do with game dev, and he has interactive examples for things. So if you look at this hexagonal grid, for instance, you can like flip things around, and there's sliders and things move. It's really cool. And of course the explanations are fantastic. And it looks like he's been working on this since, well, he says since 1995, if I remember correctly. So yeah, that's a long time. Anyway, there's this one here, polygonal map generation, and this is what we're going to be working towards. So the first part of this is start with a graph structure made of polygons. And how would you do that? Well, you have to generate a bunch of points. And I thought, okay, what's some nice algorithms to generate points? Well, I don't know any. So I started looking around, and I found Poisson disk sampling. So I'm going to be using that. And then kind of working through these steps and showing you guys how it all works. And also, I'm going to be launching my own kind of interactive demos as well very soon, so that'll be linked in the description as well. I'm not going to copy the same content as Amit if I can help it, because I think that would be, kind of a waste of my time when he's done such a good job. But if there's holes in the articles here, and there's some things that I'm doing that are a bit different, then I'd love to share that with everyone. So that's what I'll be doing. Yeah. So that's what this is for. This is to eventually end up with something like this. This is a Voronoi diagram. He doesn't really explain how he generated the island, so that's going to be an interesting journey. And yeah, this will be used for map generation, but as I said earlier in the video, you can use it for all kinds of things. Yeah, this is just what I'm going to be using it for. So yeah, stay tuned for that, and I'll see you in the next one.